Okay, so today we're going to be trying to evaluate this integral here. Some may recognise it as the gamma function, which is a useful function in mathematics in order to equate factorials. But why is that exactly? So it's not exactly the gamma function, we're just going to call it gamma hat, which is the same as gamma, but with an n instead of n plus 1, purely to make life a little bit easier. So the first thing we can do with this integral is try to integrate by parts. And for those not comfortable with this idea, is applying this formula here, which looks a bit complicated, but I'm just going to do a quick check to prove that it's okay. So first, differentiate both sides. You see the integrals cancel out, and we just have to differentiate this side in here. Well, using the product rule, differentiate that to be equal to this, and the u prime v's cancel, and we're just left with uv prime plus uv prime. Quite simple, shows that it works. Okay, if you apply this formula to this, we're going to have u is x to the n, du by dx, or u prime, is nx to the n minus 1. We can have the derivative of v to be e to the minus x, and v just being minus e to the x, giving us this. Okay, so later on I'm going to cancel out some things. So if you notice there's two minuses, those are going to cancel, and in that integral I can take the n out to the front. But for now, we're just going to focus a little bit on the left. Yeah, so the first thing we're going to do is just plug in the limits. I mean, you can't exactly plug in infinity, but we're going to do as close as we can. We're just going to take the limit as x approaches infinity, and that leaves us with this. This side we plugged in 0, that's 0 to the n, that's 0. That's 0 times minus 1, which is going to get 0. Which leaves us with this right here, which is a bit hard to work with. So first step, take out the minus, because it makes things a bit easier. And then we're going to take that e to the minus x and rewrite it as 1 over e to the x. So we get this, which is a lot easier to work with because now we can apply L'Hopital's rule. So you differentiate the top and the bottom of the limit and you get the same limit. So if you do that once, you get n times x to the n minus 1 over e to the x. You notice e to the x does not change, for it is its own derivative. This means that we can keep doing this over and over and over again until we get x to 0 or 1. We end up with this, which is the limit as x approaches infinity of some constant over e to the x. That e to the x is just going to keep growing, that constant is going to stay constant, and we're just going to be left with 0. So that means we can transform this into this, which is very similar to the integral we're starting with, except for instead of an n, it's got an n minus 1 and it's all times by n. So we can write this identity here. Gamma hat of n is equal to n times gamma hat of n minus 1. So you can see where the factorials start to come in now. So if we take an example, we say gamma of 4, well that's 4 times gamma of 3, which is 3 times gamma of 2, which is 2 times gamma of 1, which is 1 times gamma of 0. So we say that gamma hat of n is n factorial times gamma hat of 0, which is not too bad, because now we just need to find out what gamma hat of 0 is. We can see where the relation comes. So gamma hat of 0, well that's just this. Anything to the 0th power, that's just 1, so we get this integral, which is basically just finding this area right here. This area is the same as finding this area, which is the area under e to the x, and one of the defining properties with the function e to the x is that the height at some point is the area underneath that point. So this is just going to be 1. So we get the gamma hat of n equals n factorial times gamma hat of 0, where gamma hat of 0 is 1, so gamma hat of n is just n factorial. That leaves us with this integral right here. So the integral that we started with is just equal to n factorial. This is nice because this integral is well defined for values of n that are non-integers as well. So we've just shown for any integer it's equal in n, but it's also equal for any other non-integer if we define it to be so. So we can define factorials for non-integers such as pi and a half. And that makes this quite a useful thing for you to learn.